Light is a fascinating phenomenon that has intrigued humans for centuries. It allows us to see the world around us, revealing the beauty and complexity of our surroundings. But what is light, really? This question has puzzled scientists and philosophers alike. Light is a form of energy that travels in waves, moving through space at an incredible speed. These waves are part of the electromagnetic spectrum, which encompasses a vast range of wavelengths. This spectrum includes a wide range of waves, from the long wavelengths of radio waves to the extremely short wavelengths of gamma rays. Visible light, the kind we see, is only a small part of this spectrum, yet it plays a crucial role in our daily lives. Other types of light, like ultraviolet and infrared, are invisible to our eyes, but have significant effects on our world. We can, however, detect these invisible forms of light using special instruments designed for this purpose. Ultraviolet light, for example, is what causes sunburns, prompting us to protect our skin with sunscreen. Infrared light is what we feel as heat, and it is used in various technologies such as thermal imaging cameras. Light is essential for life on Earth, providing the energy needed for plants to grow and thrive. Plants use light for photosynthesis, a process that allows them to convert sunlight into energy and produce oxygen. This process is fundamental to the survival of almost all life forms on our planet. Animals, including humans, rely on plants or other animals that eat plants for food, making light a cornerstone of the food chain. Understanding light is crucial for many scientific fields, from biology to physics. It helps us study the universe, develop new technologies, and even diagnose and treat diseases with advanced medical equipment. Let's delve deeper into the mysteries of light and uncover the secrets it holds. Light has a peculiar nature. It behaves like both a wave and a particle. This duality is a fundamental concept in physics. As a wave, light exhibits properties like diffraction and interference. Diffraction is the bending of light as it passes through an opening or around an obstacle. Interference occurs when two or more waves interact with each other. Light also behaves like a particle. These particles are called photons. Photons are tiny packets of energy. The energy of a photon determines the color of the light. High-energy photons correspond to blue or violet light, while low-energy photons correspond to red or orange light. The dual nature of light was a revolutionary discovery. It challenged classical physics and paved the way for quantum mechanics. This new understanding of light has had profound implications for our understanding of the universe. Light travels at an incredible speed. In a vacuum, it zips along at approximately 299,792,458 meters per second. This speed, often denoted by the letter c, is a fundamental constant in physics. It's the ultimate speed limit in the universe. Nothing can travel faster than the speed of light. This limit has profound implications for our understanding of space and time. Einstein's theory of special relativity is based on the constancy of the speed of light. The speed of light is crucial for many scientific calculations. For example, it's used to determine distances in astronomy. By measuring the time it takes for light to travel from a distant star to Earth, astronomers can calculate the star's distance from us. We perceive the world around us in a vibrant array of colors. But have you ever wondered how color is created? The answer lies in the nature of light itself. White light, such as sunlight, is actually a mixture of different colors. Each color of light has a different wavelength. Red light has the longest wavelength, while violet light has the shortest. When light passes through a prism, the different wavelengths are bent at slightly different angles. This separation of light into its different colors is called dispersion. The result of dispersion is a beautiful spectrum of colors, much like a rainbow. Rainbows are formed when sunlight is refracted and reflected through raindrops in the atmosphere. The colors we see are determined by the wavelengths of light that reach our eyes. Section 5. Bouncing back light's reflection. Reflection is a familiar phenomenon. It's what allows us to see ourselves in a mirror. But how does reflection actually work? When light strikes a surface, it can be reflected, absorbed, or transmitted. The type of surface determines what happens to the light. Smooth, shiny surfaces like mirrors reflect light in a predictable way. This is called specular reflection. The angle of incidence, the angle at which the light hits the surface, is equal to the angle of reflection. Rough surfaces, on the other hand, scatter light in many different directions. This is called diffuse reflection. Diffuse reflection is why we can see objects that don't emit their own light. We see them because they reflect light from other sources, like the sun or a lamp. Section 6. Bending the rules. Light's refraction. Refraction is the bending of light as it passes from one medium to another. This bending occurs because light travels at different speeds in different materials. For example, light travels slower in water than it does in air. When light passes from air into water, it slows down and bends towards the normal. The normal is an imaginary line perpendicular to the surface at the point where the light enters. Conversely, when light passes from water into air, it speeds up and bends away from the normal. Refraction is responsible for many optical illusions. For example, a straw in a glass of water appears to be broken at the waterline. This is because the light from the straw is refracted as it passes from the water into the air. Section 7. Spreading the waves. Light's diffraction. Diffraction is a fascinating wave phenomenon. It demonstrates that light doesn't always travel in straight lines. When light encounters an obstacle or passes through a narrow opening, it spreads out. The amount of diffraction depends on the wavelength of the light and the size of the opening. Diffraction is more pronounced when the opening is comparable in size to the wavelength of the light. This is why we can hear someone talking around a corner even though we can't see them. Diffraction is a key concept in understanding how various optical instruments work. For example, the resolving power of a telescope is limited by diffraction. This means that there's a limit to how close two objects can be to each other and still be distinguished as separate objects. Section 8. Seeing the light. Human vision unveiled. Our eyes are remarkable organs, intricately designed to capture and process visual information. They allow us to perceive the beauty and wonder of the world around us, from the vibrant colors of a sunset to the intricate details of a blooming flower. But how do our eyes actually work? What is the science behind this incredible sense? The process of vision involves a complex interplay of light, biology, and neurology working together seamlessly. Light enters the eye through the cornea, a transparent outer layer that acts as the eye's window to the world. The cornea bends the light, which then passes through the pupil, an opening in the center of the iris, adjusting to control the amount of light. The iris, the colored part of the eye, controls the size of the pupil, regulating the amount of light entering the eye, much like a camera aperture. The light then passes through the lens, a flexible structure that focuses the light onto the retina at the back of the eye, ensuring a clear image. The retina contains specialized cells called photoreceptors, which are sensitive to light and crucial for vision. There are two types of photoreceptors, rods and cones, each serving a unique function in our vision. Rods are responsible for vision in low-light conditions, allowing us to see in dim environments, while cones are responsible for color vision and visual acuity, enabling us to see fine details and vibrant hues. When light strikes the photoreceptors, it triggers a series of chemical reactions that generate electrical signals, a process known as phototransduction. These signals are transmitted to the brain via the optic nerve, where they are interpreted as images, allowing us to understand and interact with our surroundings. Section 9. Light's toolbox, technology and beyond. Light plays a crucial role in countless technologies. From lasers to fiber optics, light-based technologies have revolutionized our world. Lasers, which emit highly focused beams of light, are used in a wide range of applications, including telecommunications, medicine, and manufacturing. Fiber optics, which transmit light through thin glass fibers, have greatly increased the speed and bandwidth of communication networks. The internet, as we know it, would not be possible without fiber optics. Light is also essential for scientific research. Microscopes use light to magnify tiny objects, allowing scientists to study the intricate details of cells and other microscopic structures. Telescopes use light to observe distant objects in space, providing us with invaluable insights into the universe. Section 10. Light's grand stage. The Universe Illuminated. Light is not only essential for life on Earth, but it also plays a fundamental role in the universe as a whole. It is the medium through which we perceive the vastness of space and the wonders it holds. Stars, like our sun, emit vast amounts of light and heat, illuminating the cosmos. This light travels across the universe, carrying with it stories of distant worlds and ancient events. By studying the light from distant stars and galaxies, astronomers can learn about their composition, temperature, and motion. This light acts as a cosmic messenger, revealing secrets of the universe. The study of light from distant objects has led to some of the most profound discoveries in astronomy. It has unveiled the mysteries of black holes, the life cycle of stars, and the vast structures of galaxies. For example, the observation that light from distant galaxies is redshifted provided evidence for the expansion of the universe. This redshift is a key indicator of how galaxies are moving away from us. This discovery revolutionized our understanding of the cosmos and led to the development of the Big Bang theory. It provided a framework for understanding the origin and evolution of the universe. Light also allows us to study the early universe. By examining the light from ancient stars and galaxies, we can peer back in time to the universe's infancy. The cosmic microwave background radiation, a faint afterglow of the Big Bang, is a treasure trove of information about the universe's earliest moments. It provides a snapshot of the universe when it was just a few 100,000 years old, offering clues about its initial conditions and subsequent evolution.